So it's my pleasure to introduce Wiygul. He's now in Trento and a postdoc of Alessandro Callotto, the PhD of Callotto, and he's going to take with us for the next Wednesday. And these videos, he's going to do a series of 3 lectures about the Lawson symmetries. Today, the first one about the uniqueness. Okay, thank you very much.
Well, thank you very much. It's a pleasure to be here and a privilege to give these talks and to get to talk to all of you. Yeah, so this first lecture will be about a paper from around 2022 with Nikos Kapouleas, who is my PhD advisor and is now a collaborator. Yeah, and actually this project was suggested to us, to Nikos, one time when he visited Granada by Professor Ross. Okay, so this is a characterization of the Lawson surfaces, the embedded surfaces of Lawson by their symmetry groups, the ambient symmetry groups, and also their topology. So I'll get started with a little bit of background and notation. Okay, so the setting is the 3 sphere, at least for most of these talks. So just the unit sphere in R4. Okay, and very often it's going to be helpful, convenient to have this notation, which is hopefully pretty self-explanatory. If I have a subset of the 3 sphere, I can take its perp, and by that I mean I take the span in R4, and then take the orthogonal complement, of the span, and then intersect again with S3. So mostly we'll be doing this with all the time when X is a great circle. So if I have C a great circle, just the trace with S3 of some 2-dimensional subspace, so some 2 planes, which is the origin. Then C perp is, you can think of it in R4 as just the trace with S3 of the totally complementary 2 planes, so the usual perp in R4. And you can think of this in intrinsic terms, in terms of the distance in S3. The locus of points of distance pi over 2 from C. Okay, so another great circle. So I'll use that notation a lot. Okay, if I have a subset of S3, I want to define a certain isometry, which is reflection. And again, X is going to be, well, not just a great circle, but typically X will be a great circle or a great sphere. But we can define it generally. So this is going to be the element of O4, which which is reflection from the span of X. So I just, if I have a great sphere, then I'm fixing a hyperspace, right? It's just reflection through a hyperplane. If X is a great circle, then I'm talking about fixing a great circle, and the orthogonal great circle is rotated through angle pi, is one way to put it. Okay, now I'll remind you of this notation as we use it, but just a little bit more. So we'll see a great circle specifically. We define T a great circle. T a great circle. And some parameter R, I'm going to find rotation along C. This is another symmetry. D. So I do a rotation in the two-sphere containing C, and I fix the orthogonal two-plane identically. And here I need, it won't really be important in this talk, the choice, but for this to be well defined, I want an orientation. So fix a directed circle. Okay, well, the choice of direction will never matter for what we're talking about. Okay, so we're in S3 and we're interested in minimal surfaces, so it's going to be a little bit convenient with this notation. So actually, I'm looking at closed embedded minimal surfaces. So closed, I mean empty boundary. Is it okay to write down here, or is it too loud?
It's okay, it's okay.
Okay, okay, and I can also specify the genus. Okay. Okay, there are two elementary examples, or of congruence, two elementary examples. The great spheres, or the totally geodesic spheres. And mostly I'll use C for circle, or often I'll use some other letters too, and sigma mostly for a great sphere. Which is the trace with the hyperspace. You can also think of it. So these elementary examples have elementary descriptions as equidistant sets. The locus of points equidistant from a point, and it's the antipolar point. Clifford tori, which we can also describe in a similar way. Okay, so we have examples of genus 0 and genus 1. And it's a famous, well, corollary of a famous result of Ambrun that actually the great spheres are all of the genus zero examples. The theorem is actually stronger, and you don't need to know this. Okay, a much more recent theorem of Brendel. Actually, the Clifford where I give all the genus one examples, assuming it benefits in this case. Okay, and I won't be using these theorems, but maybe I'll just say a little bit about the proof of Ambrun theorem because it's relevant to. It'll be useful later on. That will be useful to related material. So I want to just say a little bit about umbilicus. Okay, so if I have an umbilic on a minimal surface, then the second fundamental form will actually vanish there. Okay, and just a little more notation, which we're really just using at this point. So if I have a point on some surface, then in the three sphere by sigma pm, I'm talking about the totally geodesic sphere, which is tangent at that point. The great sphere. So I have the tangent plane, but actually I'm going to form the tangent totally geodesic sphere at that point. Tangent. Okay, so then since the second fundamental form vanishes at an umbilic point, then if I'm at an umbilic, okay, so just an observation, then I have agreement of Fn, and it's this tangent totally geodesic sphere to second order at least at B. I just wanted to introduce the notion of the degree of an umbilic. The degree, let's say D. So that's the degree. Okay. So I want the degree to be the largest integer d, so that I have agreement to order p plus 1. So if I have an umbilic, the order will be at least 1. An umbilic of order 0 is not an umbilic at all. Okay, and then using the Hopf differential, we have two important results. So one is an observation of Algorand used to prove the above theorem. So we have gamma, which is the genus. And an observation of Lawson, both using the Hopf differential. If the genus is at least one thing, and has which we happen to be. Okay. Okay, so now we can turn to Lawson's examples. Okay, so Lawson gave a construction which I'm going to describe, but I'll just give the existence statement as first and introduce a little more of the notation that I'm going to be using. Okay. Okay, so Lawson's construction gives a family of surfaces with two discrete parameters, k and m. And the notation that I'm going to be using, because I'm using the paper, the indexing does not quite agree. There's a shift in both of them from Lawson's. And so I'm going to be using m for the Lawson surfaces. And when, so we'll have maybe a fixed m and k in mind in most arguments. So I'll drop the m and k. But if I want to include them, I'll use brackets. Lawson called these surfaces C. And as I said, there's a shift which is for us is convenient, but is potentially confusing. So there it is explicitly. And so in Lawson's notation, the index is, the genus is just the product of the subscripts, the parameters, and for us it's a more complicated expression. Okay, so yeah, I'll give the construction soon, but maybe first a few just a few observations. And the first is just that we get every possible genus. So we have those elementary examples, and Lawson produces every possible genus in different ways in general. So we get one subfamily where you fix K to be 2 in our mixing. And in that subfamily, then you get every possible genus. Okay, and then because the genus is given as this product, I get the genus zero surface in many different ways in terms of the indexing. We do know. I said I won't use it, but we could use it if we wanted to. Omgren's result. We know that those all have to be the great sphere, some great sphere. And yeah, these can be. So I'm going to assume. So these can be interpreted as kind of degenerate cases of the construction that I'll go through, but because they are kind of degenerate, we'll be assuming. And we're just not going to worry about this case. We don't need to reconstruct the great spheres. Okay, we do also get Clipper torus. Again, we could appeal to Rendel's result. We know that it's genus 1, and these are embedded. But you can see this. That this is I wouldn't say it's a special case of the construction. These surfaces are very special. They have continuous symmetries, and none of the other Lawsons will have that. But this this is I wouldn't call it a degenerate case of the construction, but it's a very special case. Okay, and after we go through the construction, we'll be able to make this observation that I'm stating here about the umbilicus, but I'll state it now because it's helpful for distinguishing the surfaces that we're claiming exist already. So the isolated umbilicus. Okay, so if I have any umbilicus, well, for the Clipper torus, I don't, but if I have them, then they lie in a pair of orthogonally complementary great circles. Okay. Yeah, so we'll confirm this after the construction, but I'm going to have exactly this many umbilicus of these degrees. Okay, and so if k is 2 or m is 2, then I interpret this as saying I don't have any umbilicus of that type degree. Any umbilic is has a degree at least 1. So an umbilic of degree 0 is not an umbilic, but it helps to make the statement cleanly. Okay. Okay, so a consequence of this is just that yeah, I'll repeat it here. If I'm throwing out the great spheres. And two Lawson surfaces will be congruent, and by congruent I mean there exists R04 taking one to the other. So this happens only when the indices are different. So the Lawson surfaces are mostly really distinct examples.
What's the consequence of the previous?
What's the consequence of this fact?
Oh, we will see after the construction maybe.
Well, okay. So I was I stated this this fact about the umbilicus, which we'll see in the construction, and I'm claiming that from that you can see that this. I'm just pointing out that the surfaces which have different indices are really different, except for the possibility of switching the indices.
Oh,
Yeah. So you know from this fact you can distinguish the surfaces. That's all I want to say. Yeah. Okay. Okay, so the first step of the construction is just to pick a great circle C, and then also I've determined its orthogonal complement C perp. And so if I work in stereographic coordinates, then I can take C to be the z-axis and C perp to be the unit equatorial circle. Okay, so I'm trying, believe it or not, I'm trying not to use a lot of notation in the talk. But when I do use notation, I try to make it agree with the paper. Actually, we don't quite name this collection here, but in the paper we often use bold-faced characters for collections, and it's hard for me to do bold-faced on the board, so we use a hat for collection. I use sigma for great spheres, and so here I have some collection of great spheres, and so I fix the collection, and it has something to do with C. So K spheres which are going to be through C, and they're equally spaced. Okay, so again, working in stereographic coordinates, let me draw, or partially draw. In the case of K equals 2. So yeah, in stereographic coordinates, these such spheres will appear as vertical planes containing the z-axis, and I just take any integer, right? Any integer k at least 1. Well, we're going to be assuming at least 2 because we don't worry about the spheres. Okay, so I could have many of them, but I have a lot of symmetry, and so the angle is going to be in general, right? So here it will be pi over 2, and in general it will be pi over k. Between two consecutive spheres. Okay, and these also will intersect C perp at 2 k points. Yeah, so I cut S3 into 2k connected components, which I think is reasonable to call wedges. Wedge connected components. Two k points, so 4 points here, which come in antipodal pairs because each sphere will hit twice. Okay, we're also going to do a similar kind of subdivision through C perp, which the number is going to be given by m in this case. Collection. Of n spheres. Yeah, equally spaced together. Okay, I won't clutter the picture, but if I had, for example, m equal to 2, then I could choose the z equals 0 plane, and I could choose the orthogonal plane, a plane orthogonally intersecting that one through C perp would then be the unit sphere. Okay. Yeah, so the picture doesn't look symmetric, of course, but in the 3 sphere, the circles are on the same footing. So in this case, I cut using those spheres. I cut S3 into 2m connected wedge components, and I get 2m points on C perp and so on. Okay, and so these points will be the locations of the umbilicus. Well, when they could have, I guess, degree 0, that degenerate case where they're not actually umbilicus, but they will always be points on the surface. Sorry about that. I just want us to observe that if I have a great sphere in one of the collections and one in the other collection, then they're going to intersect orthogonally. Circle, which itself intersects both C and C perp orthogonally. So we get a total of kn great circles in this way. Okay, and I'm going to call the collection of them C hat Q. The Q will actually be explained. It's not important, but for consistency with the paper, so I just want to be able to refer to that collection. Okay, so if we cut by all of these spheres, we get a tessellation of S3 into okay, so I have 2K wedges when I cut through C with the K spheres, and 2M when I cut through C perp, so I'm going to get 4KM. Intersections of these wedges. And these will be tetrahedral with spherical faces. So okay, so here's a sketch of such a tetrahedron. Okay, so I have faces, kind of these lateral faces, which are which lie in the first collection, and then this kind of top and bottom face, which lie in the other collection. And the purple arcs lie on the great circles in this CQ collection, and then the other two edges of the tetrahedron lie on C and C purple. And the angle here is going to be, yeah, so actually the dihedral angle here along this edge is going to be pi over k. The one here will be over m, and the remaining dihedral angles are pi over 2 along these edges. Okay, and on such a tetrahedron, the I'll take Q, which is the purple, the union of the purple edges. Are not on C or C perp, so they come from the CQ. So Q is for a quadrilateral. Okay, so Lawson identifies this tessellation of S3 and quadrilateral, so you can form this quadrilateral in any tetrahedron. So we'll fix one. So called omega. So he finds a disk solution. Okay, and he uses the method of boring, which is the generalization, the Riemannian generalization of the Douglas method, roughly speaking. Okay, so he gets a minimal disk inside of this tetrahedron and with the purple boundary, and he establishes embeddedness. And he doesn't include a proof of uniqueness in the paper, but he refers to his PhD thesis for a way to prove uniqueness. So I have no doubt that he knew how to prove uniqueness. I've never been able to access his thesis actually, which I'd like to do today. And I'll give a proof, maybe a similar proof to what Lawson gave. I mean, probably in some sense similar. Okay, so I'll the proof will also give an embeddedness.
In this picture, the boundary of the disk is, look at the tetrahedral picture.
Yeah.
Then the boundary of the disk is correspond to the y edge. Can you forget the green one?
Yeah.
The other is a circle.
Exactly. Yeah. 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 That's right. Okay, so now I'm going to define a group. The definition is very simple. The notation is a little bit cumbersome. It's a group. It's going to be a subgroup of 4. So it'll be a group of symmetries, which is attached somehow to the in a very simple way, direct way, to this collection of great circles. So this is the again, it's all of the so this collection CQ is all of the great circles that you get by intersecting those spheres in the 2 collections. So they will, so all of the purple segments line such circles. And if you take every quadrilateral and such quadrilateral in every tetrahedron, and you take their union, it would cover the union of this guy. And the group is just going to be every reflection through, let's see, call it L. Okay, so here I'm C is taken, so I'll use L for a great circle. So reflections through all of those great circles. This is order 2 km. I have km great circles in this collection. I compose 2 of them. I get a kind of simultaneous rotation along C and C curve. And if I compose one of those with another reflection, I get another reflection again. I'm going to get 2 km. And acts transitively on each of 2 subsets of the tetrahedra. So I'm going to write them down in notation I haven't introduced yet. I'll explain it, but you can, I mean, I've only drawn one tetrahedron in the picture, but we have all of these 4 km tetrahedra. And if I reflect through one of the edges, I'm going to, from that tetrahedron, I'm going to get another tetrahedron, which is going to, well, they meet along that edge, and they don't meet along faces. And so I have a kind of checkerboard pattern on the tetrahedra. And I can index them. So I can color them red and black or something, or I can also talk about odd and even ones. Sorry?
Can you remind please what is CQ? It's a collection?
Yep. Yep. So CQ is consists of Kn. Yeah, the great circles are, so I have these, so I started with C and C-perp, then I chose great spheres. Those great spheres mark points. Another way you can think about it is the mark points on C and C-perp. So I have 2n equally spaced points on C, 2k equally spaced points on C-perp, and these are the great circles that I get by taking a point on C, a mark point on C, and a mark point on C-perp and joining them. Yeah, they're also, they contain the edges of the tetrahedra, which do not lie on C and C-perp. Okay. Yeah. And so if I do reflection for them through them, if I start with a given tetrahedron, the orbit will be half of the tetrahedron. It will be all of the ones which are at this particular color and this particular parity. So the I and the J, so I, index I, labels wedges along C. Actually, sorry, yeah, the other way around. What happens to be along C, right? So if I draw a top-down picture of the wedges, I just see this, I label them consecutively. So J equals 1 to 2K, and I equals 1 to 2M. And I correspondingly can label the tetrahedra by in the way that they intersect. So this would be in wedge I along C-perp intersected with wedge J along C. Okay, all right. Yeah, and so if I apply the symmetry group to a given tetrahedron, I'll get either this collection or this collection. Okay, yeah, that's consistent with the fact that I have order take 2km, so I act transitively, and actually I should have said simply transitively. Okay, so we take, so what Lawson does is take one way to describe it. Lawson takes this the plateau, this data with two. That just means you successively reflect through all those edges, and when you do that, you're going to get disks which lie in just one of these collections, and this is the orbit is M. The definition. So the surface that you get is going to miss, say, this collection, except for at the faces, the boundary, the edges effect. Okay. Okay. If you start with the disk in the other collection, you just get a congruent surface. Okay. Okay, so next I want to talk about getting the genus. I didn't say, but I should have said that. So Lawson proves that the plateau solution is embedded. I mentioned that. I'm going to give a proof, at least part of the proof of that. Yeah, then by the reflection principle, the M is also embedded. Is the description clear enough? Maybe the picture, I'm sure, is not, but okay. All right. I think if I try to draw the picture, it will be worse. But if it's clear, good. I won't say any more then. Okay. So then to compute the genus, you can do that using Gauss-Bonnet locally. So I mean at the level of a disk. So. Generate this. Okay, so on D. Okay, plus. Okay, this will be boundary D. Okay, and we know all of these terms except for the total curvature of the first term. So, but we can solve for it then. Right, because Q is that quadrilateral. It's a geodesic quadrilateral, right? So that each of those four sides is a geodesic. In fact, a geodesic in S3 even. And so this total curvature is just going to be given by the turn of the normal at the vertices. So we have to sum the sum lengths of the angles. So. Oops. Okay, so yeah, well, the angles again were the dihedral angles are this is this angle here. A, and over here we have pi over n. the others are pi over 2. For the quadrilateral, I mean, not the diagonal, so I have this quadrilateral. I'll just write it here. Yeah, sorry. Yeah, sorry. The angles of the quadrilateral are pi over k, pi over n in 2 pairs. I'm doing a later calculation accidentally. Okay. Yeah, sorry. Two angles pi over k, 2 angles pi over n. And this is disk, so I'm just going to get 2 pi here. Okay, and so globally I have, I'm going to use this to compute the genus, and the thing is that I know from the symmetries that the integral of the total curvature over M is going to be the integral of the total curvature over the disk times 2k, because I have two km disks. Okay, and so then we can solve it. I don't need to do it. So just to line it out to read that the genus that was claimed, the point is that you use Gauss and you have the local information that you need in the symmetries connect the two calculations. Okay. Okay, so we get embedded surfaces, we get the genus we're supposed to get, and now I made some claims about the envelopes too, and those are also straightforward to observe now. So we're looking at C and C perp, but let me just look at C. So I have these points. Okay, and here I'm drawing n equals 3 in the example, so I have so by construction. Yeah, sorry, this is K, not N. So yeah, K is the number of wedges that I have through C, and that gives me a certain number of great circles, the same number of great circles passing through those points which lie on the surface, right? We generated the surface, each patch contains the quadrilateral. When I apply the symmetry group, I get all of those great circles, so all of those great circles are on the surface. And so if I have more than 2, I get an another point, and I know the degree is going to be at least given to me by the number of lines that I have passed through, great circles rather. Okay, and similarly, the point is just you have these great circles and these symmetries. You know that you have ability of at least a certain degree, but then we know that we have total degree. We'll get out of this form from the Hoff differential observation earlier, and so you can check that actually these will be all of the amounts and all of the degree. So that these lower bounds are sharp. Okay, so that's my overview of Lawson's construction. And now I want to start to look at the characterization that Nikos and I have. And so this will also be useful preparation for the index material in later talks. Okay, so yeah, so I mentioned that Lawson claims the uniqueness of the disk. The proof is not in the same paper. So I'll give you a proof that Nikos and I wrote, and also will give us a certain graphicality, which I'll explain. Okay, so I'm going to, yeah, so I have again, we have now constructed the Lawson surface. We'll pick just one tetrahedron, which intersects the surface of the interior, and we'll look at the disk there. Okay, so this is my tetrahedron omega with those the four spherical faces, right, coming from those collections, and I have the all of the edges are great circles. These edges are special. They give me Q. And these other two edges are on C and C curve. Okay, so Q is contained in the surface, remember, and C and C perp are not. But it's a discrete set of points where the surface meets them. Okay. So I have this tetrahedron, and now I want to consider, yeah, so we picked these collections of great spheres to do the construction. And those great spheres determine the boundary, basically, the tetrahedron where you solve, and also the boundary too. And now I want to look at other great spheres. Namely, I want to look at the bisectors. So if I look at the edge C, the edge along C, then I want to take the great sphere through C, which bisects these two faces that meet there. So we form the bisectors. Two rates. Here's one, the bisector here, and also the bisector through the C-verb. And so these great spheres cut the tetrahedron in half in different ways along different circles. Okay, and they intersect. I guess it could use right as well. So I have also a bisector here. That's but what I want to point out is that they intersect. Their intersection gives me a great circle. So these bisectors are orthogonal to one another. Orthogonally. And this great circle, it runs from, well, it's a great circle, but the intersection with this tetrahedron omega it runs through the midpoints of the edges on C and C-verb, which we'll call the axis. And I'll call, in this discussion, I'll call this L, great circle. L, which we'll call the axis. Okay, so I take that great circle, and now I'm going to look at the rotations along that circle. And we'll let K killing field. Yeah, so I'm going to look at the rotations which fix L perp, the totally orthogonal circle, which is up here somewhere, and rotates along this L, and we can pick a direction. It doesn't matter, but maybe this way. Okay. Now I'll make a series of planes which you can check in various ways. You can do the computation explicitly, but there are many shortcuts, so hopefully they're plausible, but we can talk about them certainly. So each orbit of K I claim intersects each face of omega. So I have the four triangular spherical faces. If I take any orbit, so one orbit of this killing field is going to be this circle itself, right? The great circle, the other orbits are going to be circles, but not great circles. Okay, and so I look at these orbits, and they're going this way, generally speaking. And I claim that each one intersects each face, and at most 1 point. One way to check that is, well, the orbits are circles, yeah, circles, not great circles, but circles. And while these faces live in great spheres, and so, well, there are not so many possibilities. Either you have an orbit which is on one of these spheres, which is not going to happen because of the angles, entirely on, or you can have intersection at 1 point or 2 points. But there are certain symmetries. So you have more spheres in the picture. So there's a sphere along C, which is orthogonal to this bisector. And that's going to preserve the top sphere. Excuse me. There's the great spheres that contain the top and bottom faces are preserved by reflection through that one. And you can see that if you have an intersection point here, the other intersection point will be on the other side. So our arguments like that. There are simple ways to verify this. Okay, so that's one claim. What else? Okay. I also know that these bisectors will be preserved by the flow. They each contain the axis. That's how we identify the axis. And so I'm not going to be able to have an orbit which say starts on this side of this bisector and goes to the other side. And so using these two facts, so a little bit more to the argument, but not very much. There's very little to check. But using those facts, it follows that and if I have an orbit which hits Q, a boundary point, it doesn't hit omega anywhere else. So all of this is explicit. You can calculate it, but it's straightforward to check. Okay. Okay, so now I'm going to show uniqueness and also with the same argument, almost simultaneously graphicality. So I suppose that I have the disk, the Lawson disk D, at least a Lawson disk D. Maybe there are others, but and suppose that I have some other surface, maybe another disk, but I don't actually even need to assume that it's a disk, but I do assume that the boundary is Q. The same, and I could take E to be D in this argument. So I just have these two surfaces. Okay. And we're going to do now a maximum principal argument using these the rotations along L, along the axis. Okay, so yeah, we're doing a maximum principal argument. So we're imagining taking one of these surfaces, say E, and rotating it away and rotating along L. This is the notation from the beginning. And I know from the fact that I just wrote down that the boundary of D is not going to intersect with this rotated E, so that the boundary of D won't hit this surface anywhere in the interior or the boundary, except when you're not rotating at all. From that last fact. Okay, and also I can take omega and rotate it completely out of itself, so that they're disjoint. So I can take E and I can move it so that there's definitely no intersection between the two surfaces, and then I can start rotating back. I look for the first contact when I come back. And so by the maximum principle, and this fact that an orbit through the boundary doesn't intersect anywhere else, I know that. So if I have a first contact with T positive, I'm going to have tangential intersection in the interior, and so I know from this and the connectedness of the surfaces that the surfaces would coincide, but that's not possible for T positive because the boundary, right? The boundary doesn't touch for sure, so we cannot have. So by the match principle and can be above, we cannot have. Okay, so we can conclude from this that there's no orbit. Setting D and E at distinct points. Okay, so the only assumptions, right? These are the assumptions about E. So I can apply this conclusion with E equal to D. And that gives me graphicality of D. So if I have an orbit, in the sense that if I have an orbit of K, it's going to intersect D in just one point. With respect to K, D, and in particular embeddedness. Okay, and then, or there are other ways to argue, but once we have that, or from alternative arguments, but again, from using the maximum principal argument. So the fact is, I don't have an orbit of K intersecting D and E at distinct points, but if D and E are not the same surface, I'm necessarily going to have that. I can't have an orbit that hits a point at E and manage to pass through the tetrahedron without hitting D. So this gives you gives us the uniqueness as well.
Maybe it's almost 2.
Yeah, so I'm stopping.
Right?
Yeah, there's another jump, but
Tomorrow?
we'll do tomorrow. Yeah.
So any question or comments?
Is there any reason to say that the most symmetric minimum surface in S3 is the number of isometers, the order of the group is smaller than or equal to something, and the top symmetry is just the Lawson case, or that not exist? I suppose for some complete genes, maybe you can conclude it.
Yeah, right. But in general, no, I don't know anything like that.
Right.
Okay, so thank you.
Thank you.